Okay, so far we've only been able to solve using Laplace transforms problems that we already knew how to solve. That is linear constant coefficient problems where the right-hand side is sine or cosine or exponential or polynomial. But now we're going to solve problems with, still has to be constant coefficient linear on the left-hand side, but the right-hand side can be more general. In particular, we're going to deal with discontinuous functions and delta functions, which are spike functions. First, we define a Heaviside function u sub a is defined as being 0 up until a, and then suddenly it turns into 1 at a from a on. And this is a little more general than it looks like, because if you want a function to be f of t up until a, let's say f of t up until 10, and then you want to switch it to g of t, then you can just write your right-hand side as f of t plus u sub 10 of t times g of t minus f of t. So it's useful for any kind of discontinuous functions. And first they calculate the Laplace transform of u sub a by itself. And I won't go through all the details, but basically all this does is change the lower limit to a, because it's 0. U sub a is 0 up until a, and then suddenly it's 1. So this is just changes that from the interval 0 to infinity to a to infinity. And then they make a change of variables and come up with this. So that's the Laplace transform of u sub a is e to the minus as over s. So that's this formula here, the Laplace transform of u sub a, which is a discontinuous function that changes from 0 to 1 at a, is e to the minus as over s. But now there's another very important formula down here that they also derive, and that is the Laplace transform of u of a times another function. And it's this, so we'll refer to this. So we're going to be using this table, have to use it very carefully, and we'll be referring back to these two formulas here. So these are the two formulas I'm just talking about. We'll worry about the second one in a minute in the next problem, but the first problem we just need the Laplace transform of the Heaviside function by itself, and the Laplace transform of the Heaviside function times a function of t minus a is e to the minus as Laplace transform of f. So let's look at an example. This is a first order problem. It's an example in your book. U prime plus y equals u sub 3 of t with the initial condition y of 0 equals 2. So it's only first order equation. The forcing function on the right hand side is u sub 3. That's the function, remember, that's just 0 up until 3, and then it's 1 from there on. So let's see if we can solve this problem. We take the Laplace transform on both sides as usual. Laplace transform of y prime plus Laplace transform of y equals the Laplace transform u sub 3, which using that formula, u sub a, the transform is e to the minus as over s, a being 3 in this case, so minus 3s over s. Then Laplace transform of y prime, as always, is s times the Laplace transform of y minus y of 0, which is 2. So we have s plus 1 times Laplace transform y, and the 2 goes on the other side, and we've still got this. Divide by s plus 1, 2 over s plus 1, e to the minus 3s over s times s plus 1. So this part's always easy, but now the hard part begins. What is the inverse transform of the right-hand side? In other words, give me a function of t whose Laplace transform is that. Well, the first term is easy enough. That's just 2 times e to the minus t. A is minus 1 in this case, s minus minus 1. Now the other one, it has this e to the minus 3s. And you look at that and you say, well, if I didn't have the e to the minus 3s, I'd know how to do this. If it was just 1 over s times s plus 1, I could find the inverse transform of that, because I could just use partial fractions. So let's just call the 1 over s times s plus 1, call that g of s, and we'll figure out what the inverse transform of g is in a moment. But That third formula says that if you have a function that you know how to take the transform and you have e to the minus as in front of it, then the inverse transform is u sub a of t times little g of t minus a, where little g is the inverse transform of big G. So that formula says if you know how to take the transform of everything else, then the e to the minus 3s, all it does is multiplies by e to the 3t and changes the t to t minus 3. Let's go back and look at that formula again. So we're using this formula backwards, and we have e to the minus 3s times something that we know how to find the inverse transform of. This is capital F, we know the little f, capital G, we know little g. So you just take the Laplace inverse transform of this, and that gives you your F, or I'm calling it G, and then you just have u sub a of t times G of t minus a. So if you know how to take the inverse transform of a function, then putting it e to the minus as in front of it, all that does is adds the e to the a of t, u to the a of t times, and then changes the t to minus t minus a. So we say if we can just find the inverse transform of big G, and we can because big G is just 1 over s times s plus 1, then the inverse transform of the whole thing is u sub 3 of t times little g of t minus 3. A being 3 here. And so we just need to find the inverse transform of big G. Well, big G is that, and that we can do by partial fractions. A over s plus b over s plus 1. You solve for a and b, and you get 1 and minus 1. So you can break that up. It's basically finding a common denominator backwards. And now we can do the inverse transform of those. That's 1 over s minus 0. So the inverse transform is e to the 0t. That's a is minus 1 there, so the inverse transform is e to the minus t. So little g is 1 minus e to the minus t, so this just becomes 1 minus e to the, instead of minus t minus 3. So everywhere you have a t here, you just replace that with t minus 3, and you're done. So basically this says that if the right-hand side forcing function is 0 up until 3 and it suddenly turns on, then the final solution is what? Well, remember u3 of t is 0 up until 3, so up until 3 this whole term just disappears and the solution is just 2e to the minus t. Then suddenly at t equals 3 this term becomes 1, so the solution is this plus 1 minus e to the minus t minus 3. Okay, the second example is from section 6.4, and here the right-hand side are delta functions, delta sub 1 minus 3, delta sub 4. And what in the world are delta functions? Well, you can think of delta sub a as just being the derivative of u sub a, because what's the derivative of u sub a? It's 0 up until a, and 0 after a, but at a it's infinite. And the integral from below a to above a is going to be 1, integral of delta, because that'd be u sub a above a minus u sub a below a, and that difference is 1. So it's basically it's a function that's 0 everywhere except at a, and at a it's infinite, such that the integral of delta sub a is 1. In other words, it's kind of the limit of a function that gets higher and higher on a smaller and smaller subset around a, such that the integral of that function is always 1. So there's a difference between 2 delta and 1 delta. The integral of 2 delta is 1. The integral of delta is integral of 2 delta is 2. The integral of delta is 1. So it makes a difference. You might think you multiply that by any constant and it's the same function because it's still infinite at a and 0 everywhere else, but it's more infinite at a if you multiply it by 2. It's not really a function, but it's a delta function that's real large at a and 0 everywhere else. And so knowing that delta sub a is just the derivative of u sub a, we can use the formula for Laplace transform of a derivative of a function is s times the Laplace transform of that function minus the function at 0, well, u sub a at 0 is 0 because it's 0 up until a. So that disappears, and you just have s times the Laplace transform of u sub a. So the s's cancel, and you just get e to the minus as. So the Laplace transform of delta sub a is just e to the minus as. So that's where that formula comes from in the Laplace transform table. Laplace transform of delta sub a is e to the minus as. Okay, so here's our problem, and what in the world does this mean, though? You can think of this as a spring problem with frictional coefficient of 2 and spring constant of 3, and the external forcing. What's going on here? Well, up until 1, nothing's going on. At 1, you hit it with a hammer with a certain force in the positive direction, and then nothing happens until 4 seconds, and then you hit it with a hammer 3 times as hard in the downward direction. So, there's a difference between delta sub 4 and minus 3 delta 4. The minus makes it in the opposite direction, and the 3 makes it 3 times as hard, because even though it's infinite at 1, this is infinite at 4 and 0 everywhere else. It's more infinite at 4 if you multiply it by 3. The integral is 3 instead of 1. And the value and derivatives are 0, fortunately. Keep this thing simple. So nothing happens until 1, and you hit it with a hammer in the upward direction, and nothing goes on until 4, t equals 4, and then you hit it with a hammer 3 times as hard in the negative direction. So what's the response here? Well, take the Laplace transform on both sides, and we just saw that the Laplace transform of delta sub 1 is delta sub a is e to the minus as, a being 1 here. Then you have minus 3, and now a is 4, so it's e to the minus 4s. So that's pretty straightforward. And factor out, the Laplace transform of y double prime is s squared Laplace transform of y, since the y and y prime are 0 at 0, so those terms disappear, and so does this one. So you just have s squared plus 2s plus 3 times Laplace transform of y. Divide by s squared plus 2s plus 3, and you get Laplace transform of y equals this divided by s squared plus 2s plus 3 minus 3 times e to the minus 4s over that. Well, you look now, how comes the hard part, finding the inverse transform of these two. And you say, well, if only I didn't have the e to the minus s, I know how to find the inverse transform of 1 over s squared plus 2s plus 3. And so I'll just write this as e to the minus s times g of s minus 3 times e to the minus 4s times, it's the same function here, fortunately. So if I can figure out what the inverse transform of g of s is, where g of s is 1 over s squared plus 2s plus 3, then once I find it and call it g, little g, then the inverse transform of this is little g of t minus 1 times u sub 1 of t. Inverse transform of that is u sub 4 of t times g of t minus 4. In other words, e to the a minus as g of s, the inverse transform is u sub a of t, g of t minus a. So all I have to do now is find the inverse transform of big G, and I'm in business, so here it is. Here's big G. If you could factor it, you factor it and use partial fractions, but you can't. You complete the square. It's take half of the 2s and square it, and you need a 1 there, so s squared plus 2s plus 1 is s plus 1 squared. That leaves 2 over 2 here, and 2 can be written as the square root of 2 squared. So now we look at our table and look for something of the form 1 over s minus a squared plus omega squared, and there's a couple of them. Well, this is the one we want because the cosine one, this one, the cosine one has an s in the numerator. We don't have an s. We've got a constant. It's not the right constant, but that's easy to change. So we need omega over s minus a squared plus omega squared, and the inverse of that is e to the at sine of omega t. So we're going to read this one backwards. We have to manipulate our right-hand side into this form. You know, it's a lot like using integral tables. It's not as easy as it sounds. You look for something that's as close as possible to what you have and try to manipulate it to where it's exactly what you have. And we should be able to get it into that form. Omega over s minus a squared plus omega squared. Well, that's just what we have, s minus a squared plus omega squared, except we need an omega in the numerator, and we don't have it. Well, omega being square root of 2, I just put a square root of 2 and divide by the square root of 2, and now this is omega over s minus a squared plus omega squared, where a is minus 1, omega square root of 2, and the inverse transform of that, according to that table, is e to the a being minus 1 t sine of omega t, and then I've got the 1 over the square root of 2 there. So we were able to find the inverse transform of this. Therefore, we can find the inverse transform e to the minus s times that. It's just a use of 1 of t times little g of t minus 1. And then the same thing here, except this is use of 4 of t, g of t minus 4. So we've got use of 1 of t times little g of t minus 1. That means just go back and plug in, replace t by t minus 1. So you got 1 over the square root of 2 times e to the minus t minus 1 sine of square root of 2 t minus 1. The other one, we've got the 3 there, and then we've got the square root of 2 from here. Use of 4 times g of t minus 4. So replace t by t minus 4 this time. And there's our final solution, which says that up until 1, both of these terms are 0, so the y is 0 until 1 because nothing happens until 1. Then this term turns on, so this just becomes 1 times that. And then at 4, this one turns on, and altogether, there's your solution.